So the last topic that I'm going to tell you about is rationalization, which is like a very useful technique. You never need to take like pre-calculus or calculus. Um, that's what useful thing to know how to do. So let's talk about that. Um, so the idea of like rationalization is how to rewrite um, a fraction that has one term, either the numerator or the denominator involving a combination of square roots. So let me just kind of like to make this a little more concrete. So, so the goal here is to rewrite a fraction where it's either the numerator or the denominator has two terms, and least one of which is a square root. Okay. So that sounds a little bit weird. So let me kind of like try some examples so that you can see the type of stuff that I'm referring to. So here are some like expressions that you might care about. So one would be something like 1/√3 plus √2. Okay. So if you look at that, it's a fraction, right? And the denominator involves two terms, right? Like this term, and both of which are like square roots. So there's nothing wrong with that like expression. It's just like a number that's perfectly fine. Like if you could leave the answer like this, like that is like legitimate. It's just that sometimes if you want to understand what the number is, it can be convenient, like on occasion, to rewrite it in a certain way. And that's what rationalizing the expression will do for you. So like I'll tell you, like teach you how it works, but once you rationalize it, you'll see it looks a lot more understandable what the answer is supposed to be. Here's another one that is kind of similar. You could have something like okay, so like again, in fact, there's nothing like specific to this being one. Like you could put something like different, like x+3, with something different. So like again, like here you have a fraction. The numerator is perfectly fine. Like it has two terms. The denominator is also perfectly fine. It has two terms, but like at least one of these two terms involves the square root, and like the root of x in this case. So again, there's nothing wrong with this expression, but there are occasions where it is convenient to rewrite it in a certain way to understand a bit better what's going on. In fact, like like again, I'll tell you in a second how it is supposed to look like. So here's like an example. This is like an example where there are two square root terms in the denominator. Here's an example where there is just like one square root term in the denominator. And there's nothing specific about them being in the denominator. You could also have them in the numerator, like like the easiest way. It's kind of like to flip them, but if you could like give you other examples, you could have something like this. You could have square root of x minus 4 over these, like, again, it's kind of an example where, like, there's a fraction and one of the terms like has at least like a square root. So here's like one square root. And like there, you could also have like two square roots in the numerator. So you could have like something like square root of 2 minus square root of 3, for example. Or like again, here it can be whatever it wants. Something like this. So this is an example where like two square roots. So like the idea is like it is divided for fractions, and at least the numerator or the denominator has two terms. Uh, one of those terms being like a square root. So you can have situations where like there are two square roots of square, but at a minimum there must be at least one square root in one of the expressions. Okay. And again, there's nothing wrong with any of these. Like it is like fair game to leave the answers that they are, but sometimes for specific purposes, it is convenient to rewrite them so that it looks better, and you have a better understanding of what's going on. Like in fact, that is kind of like one of the things that you do a lot in calculus if you ever need to take it. So I'll kind of like show you kind of gets used back near the end. Um, okay, so the idea like what for rewriting this is to use the different squares like over and over and over. So like the difference of squares is kind of like one of the magic formulas for each class I have told you. So like the idea. Okay, so if you remember like the difference of square formula, it just says that a squared minus b squared is a minus b times a plus b, right? That is what the difference of square formula says. What is not super obvious is that you can actually use it for things that do not necessarily look like squares, but you can kind of force them into like a square version. So just to give you like an example, like let's just work with that. I think actually we had done that in one of the classes. So before, how can you think about this formula? Like say if I gave you something like x squared minus 4, if you have x squared minus 4, then you would say, okay, this is perfect because 4 is 2 squared. So you have x squared minus 2 squared, right? Which is x minus 2 times x plus 2, right? So like that is like an application of the difference of square formula, like a direct application, right? Now, if you have something like x squared minus 5, then you could be, okay, this is like really sucks because like 5 is not a square. But the point of like the square root is that everything is a square thanks to square roots. That's kind of like the nice thing about square roots. So you can actually think of these as being x squared minus root of 5 squared. Which is kind of like a neat trick. That is the point of a square root, like forces everything into like being a square, like in a sense. And because of this artificial, I mean, it's not like artificial, but that's kind of how it's designed. Like then you can apply the difference of square formula to this, which was not super obvious, right? Because like before, like you didn't think of 5 as a square, right? So this would give you x minus root of 5 times x plus root of 5. Is that making sense? So like many of these cases, what I'm trying to say is that when you have a difference, like even when like the number doesn't look like a square, it can be made into a square with thanks to with the square root. So like a version of the difference of square formula, just like if you just kind of follow this analogy, it's something like a squared minus b, would be like a minus root of b times a plus root of b because of what I just told you. So this is essentially another way of rewriting the difference of square formula, right? It just doesn't look as elegant, but it's kind of like the same idea. Does that make sense? So, like, here's another one, like, there's nothing specific about the second one, like, you could have used the same idea for the first one. So, for example, if you had like x minus 4, well, here I do have to think that x is not negative, but let's just like say that that's the case for now. Then you could say, well, this is like root of x squared minus 2 squared, right? Again, I can assume that x is positive, so that this kind of does work fine. So if you think about it from that perspective, then you can apply the difference square formula again, that gives you root of x minus 2 times root of x plus 2. Okay? So again, like the second term was kind of like a square in an obvious way. The first one, not so much, but that is the point of the square root, that like you can make things a square. So like just by analogy, like like the difference of square formula in this case kind of looks like a minus b squared equals like root of a minus 3 times root of a. Okay, so like all that I'm saying is that this is kind of like the original difference of square formula, but essentially these two are basically the same idea, but like you know rewritten in a slightly different way. That kind of making sense. So here's like a more extreme, very like you can kind of like apply the same idea to both terms. So for example, if I had given you something like x minus 5, right? What would you do x minus 5? You can think of the first one as root of x squared, right? So you think of this as root of x squared, and then as the second one as root of 5 squared, right? So again, it's like a difference of square formula. So this is like root of x minus root of 5 times root of x plus root of 5. Okay?
So you can manipulate it.
Yeah, like so essentially you can manipulate both simultaneously, right? It's not just like one that you can apply this square root idea. And like the way the formula looks in this case would be something like a minus b equals root of a minus root of b times root of a plus root of b. Okay, so all of these four versions, like you should think about them as kind of like four versions of like thinking about the difference of square formula. It's just that like kind of like the orange one is the like OG version, and then the others are kind of like you kind of massage the formula into like looking like that. Okay. That making sense so far, so okay, like so let me give you just to kind of get closer of what I meant by rewriting the expressions. This is actually like a useful idea if you want to rewrite like the fractions like that I was writing before. So for example, so here's like an example of how you can use these formulas. Let's go back to 1 over root of 3 plus root of 2. Okay, like I want to understand this in a slightly different way. Okay. So what I can do, and I'll tell you kind of like what the rule is, but what you can do is kind of multiply what's called by the conjugate of this term. Okay, and so if you think about it, what's happening here is that you have like root of 3 plus root of 2. That's kind of like what appears here, root of 3 plus root of 2, right? Like if you think of a, let's think of a as 3 and b as 2. Okay, so this is saying if you have root of 3 plus root of 2 and you multiply it by root of 3 minus root of 2, you can get rid of the square roots. Like that's kind of what it means. So what I'll do is kind of like take this fraction and I'm kind of very clever, like this is like a clever thing to do. I'll multiply by the same expression, but with like the sign reversed, like the opposite sign. So like a plus becomes a minus. Okay. like this should be with square root. Again, why? Because here, this thing was root of 3 plus root of 2. And so what the formula, the square root formula says is that if you multiply by the same thing but with the opposite sign, you will get rid of the square roots.
It'll be 3 - 2.
Yeah, at the bottom, correct, like, yes, it will be, so let's just think about what happens. When you multiply the numerators, you get 1 times this, like that's just root of 3 minus root of 2, so that's what happens, with the numerator. Right, but what happens with the denominator, like the difference of square tells you it's like, just like 3 minus 2, basically, so I'll write it like this, like it's root of 3 squared minus root of 2 squared, like, so that it looks more clear, like more obvious that it is like the difference of square root formula that I'm using. Is that the root of 3 squared is 3 and root of 2 squared is 2. So like this is 3 minus 2. And 3 minus 2 is just 1. So essentially, what you end up finding, like it's kind of like worth like writing this as like what we just found. Like what you end up finding is that 1 over root of 3 plus root of 2 is root of 3 minus root of 2, which is like highly not obvious, right? If you look at it, like it's kind of surprising that this is actually the case.
Is it the reciprocal?
Mhm.
No, right?
No, it's not the reciprocal because the reciprocal would be with the same sign.
Right, okay.
Right. So it's not the, like, that's the thing, right? Like, it's not the reciprocal. But it is, if you compare this expression, like, this looks a lot more complicated than this because it's just like here, like, it's not even like a fraction, right? Like, the denominator is 1, if you want to think about it that way. And, you're just subtracting two square roots, whereas here, you're adding them and then you're dividing, like, you're putting that as a denominator. Like, it does look a lot more complicated as an expression, like the left side. But like, by doing this trick, you kind of like rewrite it in a way that looks a bit more understandable, if that makes sense. So, and that's essentially, that again kind of sense up to now. And that is kind of like the idea of multiplying by the conjugate. So I kind of will write now in a bit more words like what I just did. But essentially, it kind of all stems from like understanding that the structure like of these square root formulas or difference of square formulas is that you kind of multiply the square, like the stuff with the minus sign and the stuff with the plus sign to get something where like the square roots disappear. So I'll kind of tell you that like in words, like put it here. Like, so the main tool, like, to rationalize something, what you do is multiply by the conjugate. And I'll just give you like a table of what the conjugates are. To rationalize a fraction, you multiply by the conjugate of the expression that has the square root. Conjugate. So let me put it like a table because like that's kind of easier to understand. So for example, like the first one is the green one. So say if like the expression is, let's do like the sum version first, is root of A plus root of B. The conjugate is essentially what you get by flipping the sign in the middle. So there was a plus here, the conjugate of this will be the version with the minus. So the conjugate would be root of A minus root of B. Okay. And when you multiply these two, like the product between the original expression and the conjugate, it is a difference of square. So in this case, will give you A minus B. Okay. Then what is the other one? Like the other one would be with the minus version. So I don't put them with the same color because they're essentially the same idea. So if you have root of A minus root of B, the conjugate of this is the version with the plus. So it's always flipping the sign of like the middle term, and then the product is still A minus B. Okay, and then you have like the this version in like let's take the blue version next. So again, like the conjugate for any of these things is always like flip the sign. So you put root of A minus B in this case. And when you multiply these two, because of like the difference of squared formula, you get A minus B squared. Then you have like the minus version, which again, the conjugate just flips the sign. Square. And the other one, like just to continue this, like the last one is with the like. Like the last one is like the other, like the one that I have written in yellow, I think. It's like A plus root of B. So the conjugate would be A minus root of B, and when you multiply these two, you get A minus B. And then you could also do A minus root of B. The conjugate of that is A plus root of B, and you get A squared. Okay. So like the conjugate is just always flipping the sign. Or like if there was a plus in between the terms, you turn it into a minus. And if there was a minus in between the terms, you turn it into a plus, basically. Let me do a few more examples to kind of like show you how like this kind of looks in general to. And like that kind of like gives like a sense of like how like the simplifications work. So for example, let's do. To make it a bit more interesting and show you how this can be used in practice. So let's say I wanted to rationalize. So again, the idea is when you have a fraction, either the numerator or the denominator has something with square root. In this case, the denominator is the one that has like the square root stuff. Okay, so what rationalizing means is to multiply by the conjugate of the expression with the square root. So that just means flip the sign of like the term with the square root. So if like the term with the square root is root of x plus 3, flipping the sign just means turning this plus into a minus. So you multiply and divide by the same thing in the denominator, but with the minus sign instead. Okay, so kind of do x squared minus 81 over root of x plus 3. And you multiply and divide by this version with the sign flip. So actually, which of these versions? I mean, the blue case, right? In fact, like, you just have to remember to flip the sign, so you don't have to like actually remember all these rows, like just like the idea of flipping the sign. But I'll just use the same color that would match with the table. Let's put actually. Oh yeah. So again, like this is what's root of x minus 3 is what's called a conjugated root of x plus 3. So you multiply and divide by the conjugate just to leave the expression like the same. And then like like in the numerator, like the numerator, like I'll just leave it like that. Like I won't do anything to it for now. You'll see that we can do something to it like in a moment. But it's convenient to write it like that. Okay, that's fine. And what happens with the denominator? That is where like essentially like the difference of formula is. Like so you have some like that has like the structure of the difference of formula, difference of square formula, sorry. So like what you do is like square the first term and subtract the square of the second term. So the root of x squared is just x and 3 squared is 9. So that is what the differential formula is, which is what you see here, what I wrote here, like in the last column, that if you multiply these two things, you get like the first one squared, it just happens to give you a in this case, and then the second one squared, and then you subtract those two numbers. Does that make sense? And why, okay, what is the advantage of doing this? Like, so for example, this can be even further simplified because you can actually apply the difference of square formula to x squared minus 81, right? Because 81 is 9 squared. So like, let me use a different color. I can use orange because that's what I want. I use for the original difference of square formula. And like now x minus 9 is both in the numerator and the denominator. So that gives you what? X plus 9 and the root of x minus 3. Which is like just like that is good enough to more than enough. But like if you compare it, if you compare like the original expression versus like the final version, they're all the same again because they're all equalities, right? So every one of these is equal to one another. So it's all like just a kind of like a cosmetic change, like on how it's being presented. But it's just like kind of in many circumstances, it's a lot easier to understand this versus understanding this because kind of like understand you do want to kind of like get away from fractions to the extent that's possible, like not always can be done. And so like that is like a convenient way to rewrite it. Okay. Do another example. And another one here. Just to illustrate, okay, just do one with the blue one. I'll do one with the green one later. I'll do just one with the yellow. So let's just rationalize. Just to show you that it doesn't have to be in the denominator. Let's say I wanted to ration. Oh, in fact, yeah, this just to kind of make sure, like want to create yeah, this one is nice actually. Okay, this one is like how you spreadsheet one. Just like because like it kind of like will dispel certain things, like, you to show you that you can have the rationalization something in the numerator, and that it's not that root of x always has to be like the first term. You can have something with the square root on the second term, like as seen here. Okay. So what's happening now? So again, like all these problems about rationalization, it is about multiplying by the conjugate. Okay. So the conjugate is what you get by flipping the sign to the term that has a square root. So in this case, this minus turns into a plus. So basically, you rewrite the exact same expression, but with a minus, sorry, with a plus instead of a minus. So, and like this version, like you see, is the last row on the table. So I'll use yellow because it's like the same version of like there. So it's 3 like root of x over 3 square root of x. Okay. So again, the conjugate just flips the sign from minus to plus in this case, because there was a minus or in the original expression. Yes.
For the top,
Mhm.
I have to get x minus 9 and x plus 9.
Uh,
Oh, wait, is that a whole different thing?
oh no, like this is like from the previous example.
Oh, okay.
Yeah, like let me erase it actually to prevent any misunderstanding. So yeah, so here I'm just flipping the sign. And then what the formula says, is that when you do the product now in the numerator, this is like the difference of square formula. So you take the square of the first term, the square of 3 is just 9, and you subtract the square of the second term, the square of root of x is x. So you get 9 minus x here, which is again, like you see, it is basically like that. And then, like, there's something that can do the denominator. But in fact, like, essentially, my intent was like, just, this is fine, like, this would be the end of this problem. But to make it slightly more interesting, like what I should have put here is like an 81. So let's say if I had put like an 81 here, sorry about that. So if we put like an 81 here, you have 81. You have 81 now, and then you have 81 here. Okay. Why is like the nice thing about putting an 81, so that you can apply the difference of square again to that one. Just to kind of like keep practicing like this like factorization techniques. Like you get here like x minus 9 times x plus 9, right? Then 3 plus root of x. Yeah, then you can take a -1, like like 9 minus x and x minus 9 are almost the same, right? They just differ by an overall line. So that's also like why I wanted this example to go like that as a practice. Like so like you can write it as x minus x minus 9. And now these minus signs do go away, sorry, not the minus signs, like this term. Is the same here as in here, so you get -1 divided by x plus 9 over 3 plus root of x. So again, like, it just gives you like a different perspective on how this fraction looks like. Uh, Because now, for example, everything that has x is concentrated in the denominator. Yes.
So in the example that you had before,
Mhm.
where it was
With 9.
yeah,
Uh-huh.
so would you have even bothered to put a factor
I
there if
mean,
it doesn't
right.
change anything?
Yeah, like you could have like, in this case, like wouldn't have made much of a difference, like you could just have left it as that, because yeah, you could have rewritten that as x minus 3 times x plus 3, but then there's nothing else that can be canceled out. So like, it's kind of, there is more like up to you whether, like, like factoring kind of makes sense if there's cancellations involved, but, which is why I have to change it to kind of keep canceling. So yeah, x squared minus 81, sorry, x squared minus 9 would have been fine to just leave it as it is. Um, but, but yeah, like if that had been, like, for example, you could have had this term be subtracted to another fraction or something like that. Or maybe you have to combine the denominator, like use like the common denominator stuff, in which case like it would have been convenient to do that. But yeah, like, usually like factorization is useful to the extent that you can cancel things or simplify things. So in that case, that wouldn't have made much of a difference. But yeah, like, that's why I had to make a small change in that problem to make it more interesting. Okay, but like again, like the point is that the conjugate really is just flip the sign. Like there's nothing like else to memorize really, like except like you change a minus to a plus or a plus to a minus. And it doesn't matter whether like, the square root is in the numerator or the denominator. It kind of is always the same idea. Let me do an example where like there are two square roots, because it's actually like more like related to like the calculus perspective. So yeah, let's do this one. Let's say I have something like this. So again, what is going to happen here? So you want to rationalize this. So again, you just identify the stuff with the, like the term with the square roots, like in this case happens to be the numerator again. So you turn the minus into a plus. And in fact, it is like the first two versions, right? Like it's the green version, like it's like a difference of square roots. So like we're in the, like the second row case. So I'll put it like this. Oops, like there should be a minus. Yeah. So it's the green version, so minus turns into a plus. So what's going to happen here? Again, for the numerator, like you have like the difference of square formula, which is it's like the square of the first one, root of x squared is x, minus the square of the second one, root of 5 squared is just 5, so it's x minus 5. And there's nothing like much else that you can do to the denominator, so I just read it as this. But then what happens is that x minus 5 is present in both the numerator and the denominator, right? So you can remove it. Okay, like the same here as in here. This gives you 1 in the top, so you get 1 over root of x plus root of 5. Okay. So in other words, it's kind of like useful to kind of put this like as a single, like just like to write what we just found. So we just found the root of x minus root of 5 over x minus 5 is 1 over root of x plus root of 5. That makes sense. Okay, so why is like this is kind of like useful beyond like kind of like the aesthetics of whether like this looks nicer than this. It's not just like whether one looks better than the other. It's just that like again you'll see this if you ever need to take like calculus or pre-calculus maybe. But like the things like by rewriting the formula in different ways, like it kind of gives you extra information. So for example, like this version of the equation, there is no way to make sense of what the value for this should be when x equals 5. So what happens if you try to put x equals 5 in this equation? If you try to plug in x equals 5, right? Well, the issue that you have is like the denominator would become 0, right? Because you get 5 minus 5, which is 0. So you get, well, you get like root of 5 minus root of 5 over 5 minus 5, which is very undefined. Like it gives you 0 over 0, right? And 0 over 0 is not 1, just in case. Like there's nothing that you can say that's useful about what this should be. Like you kind of have to stay away from something like this. It's like danger zone. So like this is like bad. Okay, so you don't try to give a meaning to something like that looks like 0 over 0 directly. Like say you plug x equals 5 here. But by doing this manipulation, like acrobatics of like multiplying by the rational, like the conjugate and things like that, is like this is kind of like more like tame near like x equals 5. Like if you put like x equals 5 here, um, what do you get? You get 1 over root of 5 plus root of 5, right? Which is just 1 over 2 root of 5, which is, there's nothing wrong with that. It's just like a number, right? So in fact, like kind of like the point of doing calculus, like to a large extent, is kind of like to do a bunch of this stuff over and over. So you get things that originally, if you have tried to evaluate it at certain values, give you nonsense, like 0 over 0. But then by doing like math, like some trickery, like you might rewrite them into something where you can just plug in and it gives you something useful. Like so in calculus, you kind of like do this, I can put in like a more fancy notation to kind of like impress people. So you just write something like that's called the limit. So you would write something like the limit, as x approaches 5 of root of x minus root of 5 over x minus 5 is 1 over 2 root of 5. Which is just like a very nice way to say, if you just manipulate this, and then you can plug in and then you get this number. So it's kind of like a very fancy way of saying it. And then like it looks confusing, like if you have never seen this before. But that's again, if you ever have to take calculus, that would be kind of like the bread and butter. So that is like what makes it work in a sense, like the fact that you can take an expression, like manipulate it in different ways, and kind of surprisingly, if you look at it from a different perspective, it does make sense, like what the value, like, which is kind of like, again, it is like a weird thing that would happen. So, but it's like a good example to kind of keep in mind if you ever see it later, because like, oh yeah, like we kind of like did a bit of that before. Okay, so yeah, like this is somebody says. Okay, so yeah, like this is a kind of like the last thing I needed to tell you about. So let me close here.